Thank you for joining us on another episode in solving ODEs. So in this episode, we want to focus on how do we actually use the convolution to solve an ODE. Last time I defined it for you guys, and we computed the convolution of two functions. So now in this episode, what we're going to be doing is we're going to be looking at a concrete example, and we're going to use this to solve this ODE. So in this ODE, what we're looking at is we're looking at x to the third power, and this is equal to the Heaviside function shifted times 2. And then we have initial conditions. So in all of these examples where we're using the Laplace to solve an ODE, the first step is to take the Laplace of both sides. So let me go ahead and write that here. So step 1 would be to take the Laplace of both sides of this ODE in which you want to solve. So I've already done part of it. So in doing this, in practice, you're using a lot of tables. So it's important to understand the method and how to use your tables. So here is the Laplace transform of the third power. So we have here capital X, which is a function of s, which is the Laplace transform of little x, and then you have little x at the initial conditions, first derivative and second derivative, and I forgot to mention one more initial condition, and that was that at the second derivative, valued at 0 is 0. So in this case, in this situation, this entire thing is going to collapse into s to the third power times the Laplace transform of little x. On the right side, we want to take the Laplace. So the right side is going to be, so let me put this in so you can see it. So the Laplace transform of what we have here is going to be 2 times the Laplace transform of the Heaviside function shifted, which is going to be e to the negative sa divided by s. All right, so after you take the Laplace transform, step 2 is going to be solve for capital X. So we're interested in little x, but first we want to solve for capital X. So this isn't too difficult to solve. And so what we have here is 2 times e to the negative sa divided by s to the 4th power. All right, the last step, step 3, would be to take the inverse Laplace of both sides. Because on the left, what is the inverse Laplace of capital X? Well, it's going to be little x. That's how we define these. That's the function we're interested in. And what we're looking here is at the inverse Laplace of 2 times e to the negative sa over s to the 4. All right. Now what we want to notice here is that on the right here, we can split this up in the following way. We have here the inverse Laplace, but on the inside, we can split this up as 2 over s to the third power times e to the negative sa over s. And this looks familiar, okay? This here, let me switch some colors to make things more exciting. So looking at this on the right, that is the Laplace transform of the Heaviside function shifted. On the left here, we also know the Laplace that is the Laplace transform of t squared. So it would be nice if we had a formula connecting the two. But wait, Don't worry, we do. We have this neat formula, which we talked about just a little bit last time. But in this time, we want to use this formula here. We know that the Laplace transform of the convolution of f and g is just the product of the two. So how is this useful? Well, it's useful because just take the inverse Laplace of both sides, and we're going to get that f times g, not times, but the convolution of the two is going to be the inverse Laplace of. So in this particular case, we want to apply this to this example. So what we write here is the Laplace of t squared times the Laplace of the Heaviside function shifted. Awesome. This is useful because now we know what x is. So it turns out, erasing this, it turns out that x, so connect the equalities, this is exactly what x is. X, the solution, is going to be the convolution of t squared and the Heaviside function. So last time we computed what this is, so let's go ahead and scroll up a little bit, not going too far. Copy. Scrolling back down to our answer. And this is what we get. We get that our solution to the system of ODE, our solution to our ODE is exactly this here. So thanks for joining us.